Welcome to ICG India. Here we upload technical course on mechanical engineering, electronics engineering, and computer engineering. We also upload tutorial on programming language, software, and engineering mathematics. In this video, we are going to discuss about the basic formulas used in vibration. This is very important because if you know all the basic formulas, then only you can solve any problems related to vibration. I'm going to cover the basic formulas related to free and forced vibration. So first thing, what is vibration? Any motion that repeat itself after an interval of time is called oscillation or vibration. You take a waveform like this. Any motion which repeat itself after an interval of time. After this point, it will again repeat the same motion. Then it is called vibration. There are two basic terms in vibration. First one, the number of cycles completed per unit time, that is called frequency. Let's take a waveform like this. This is 1 second. This is one complete cycle and this is another complete cycle. Take this point as 1 second. So the number of cycle completed per second, 2 cycles. So this is called frequency. Here frequency equal to 2 hertz. Unit for frequency hertz. The formula for frequency f is equal to 1 by time equal to omega divided by 2 pi. Then another important thing, time period. Time period just opposite to frequency. The time taken complete one cycle of motion. For example, in this diagram, one cycle means this is one cycle. The time taken to complete one cycle, this is maybe zero point 0.5 seconds. So in this problem, time period t equal to 2 pi by omega, zero point 0.5 seconds. So what is frequency? 1 divided by time. Here what is time? 1 divided by zero point 0.5, which is nothing but 2 cycles. I mean 2 hertz. So this is frequency. The frequency and time period are just opposite. And this is how you can find frequency and time period in vibration. There are three basic elements in vibration: mass, spring, damper. The equation for mass, F is equal to mx double dot. This is nothing but Newton's second law of motion. Then there is an equation for spring, F is equal to kx. This equation obtained from uh, Hooke's law. Then there is a third element, F is equal to Cv, Newton's second law for fluid. F is equal to Cv. Here C represent damping coefficient. Let us take a simple example. Two springs connected in parallel. In this case, what is the equivalent value of spring? K equivalent we need to find. So this is, we can easily find that force, total force equal to F1 plus F2. Here F1 represent force acting on spring 1 and 2. So total force W. So F equal to F1 plus F2. Here we know that F is equal to Kx. I can rewrite this equation as Kx equal to K1 x1 plus K2 x2. Here K is nothing but equivalent value of stiffness, then displacement constant. If spring 1 display x1 amount, same amount K2 will also deform. The same amount X will also, W will also deform. So here X equal to X1 equal to X2. You can cancel this term. Finally, K equivalent equal to K1 plus K2. This is the equivalent value of stiffness. There is no need to memorize this formula. You can easily derive this formula from free body diagram. Let's take another condition. Two springs connected in series. I'm going to apply the same free body diagram here. Total displacement equal to displacement of spring 1, displacement of spring 2, because two springs are connected in series. We know that F is equal to Kx, from that X equal to F by K. Here I can write it as F by K, F by K1, F by K2. Force constant I can cancel. 1 by K equivalent equal to 1 by K1 plus 1 by K2. So this is for two spring connected in series, whereas this is two spring connected in parallel. If two spring connected in parallel, a K equivalent equal to K1 plus K2. If two springs connected in series, then 1 by K equal to 1 by K1 plus 1 by K2. While solving problem, we use this formula. Potential energy stored in spring. Let us consider a spring where we are applying force F. Whenever you apply a force, there is a displacement X. This is the relation between displacement and force. Potential energy is nothing but area of this triangle. So how do you find area of triangle of PH? Potential energy U equal to of PH, area of triangle, of into height value force, breadth value x. Again, we know that F is equal to Kx, then of equal to Kx into x of Kx square. So total potential energy stored in spring of Kx square. So this is how we obtain potential energy stored in spring. There is no need to memorize all these formula. Once you know the concept, logic, you can easily derive this formula. Equation of motion. First, we will derive the equation of motion for free vibration when no external force act on body after giving initial displacement. Let us consider a spring mass system, MK system, where I am going to apply a force F after giving an initial disturbance. This is called after giving initial displacement. The body is said to vibrate with own oscillation. Then the vibration is called free vibration. Initially, we give some force, then we will remove our hand. Then what happened? The spring will vibrate like this. The mass will vibrate like this. This vibration is called free vibration. Then the frequency is called natural frequency. Here, the frequency will not decrease because there is no damping. It will continue forever. Practically, this is not possible, but this is called natural frequency. Actually, natural frequency omega n equal to square root of k by m. Let's see how to derive this formula from D'Albert principle. D'Albert's principle state that F is equal to ma, from that F minus ma equal to 0. Here F represents spring force. We know that spring force F equal to kx. But here minus kx, because when you apply force downward, the spring force will act upward. So kx will act upward. So that minus sign represent both applied force and spring force are opposite. That's why we put minus kx here. Then inertia force, we are applying force downward. So F equal to ma, which is nothing but mx double dot. Mx double dot. I can cancel minus on both sides. From that equation, mx double dot plus kx equal to 0. Here x double dot represent double derivative d squared x by dt squared. I mean acceleration. This is a second order differential equation. When you solve this equation, you will get omega n equal to square root of k by m. This is called equation of motion for free vibration. Mx double dot plus kx equal to 0. There is another method, energy principle. You can solve this, you can find the same equation using energy principle. Let's see how to solve using energy principle. Total energy of the system constant. So when you differentiate total energy, you will get 0 because total energy constant means d by dt of constant 0. Total energy is nothing but potential energy plus kinetic energy. What is potential energy? We already derived in the previous slide, U equal to half kx squared. What is kinetic energy? Half mv squared. Half mv is nothing but x dot. So this is x dot squared. Now differentiate this equation. I can cancel 1 by 2 on both sides. M constant, x dot squared, x double dot, 2 into x double dot. Then d by dt of kx square, k constant, 2x equal to 0. Again, I can cancel 2 on both sides. Mx double dot plus kx equal to 0. That's what we are getting. Mx double dot plus kx equal to 0. So we are getting same equation here. This is using energy principle. Sometimes in the examination, you will get questions like that. Derive the equation of motion for spring mass system using D'Albert's principle or using energy principle. Then you have to use this equation. This is called mathematical model of vibrating system. There is one more method. You can derive the equation of motion using Rayleigh method. It says that total kinetic energy equal to total potential energy. I mean, mean kinetic energy equal to extreme potential energy. What is kinetic energy? Half mv squared. Again, v is equal to omega into x. So, half m omega squared x squared because mv squared. Kinetic energy of mv square. Potential energy, we know that stored in spring of kx square. I can cancel off on both sides. Then we can cancel x squared. From that, k equal to square root of k by m. So this is how we derived natural frequency of the system. So natural frequency of mk system equal to omega n. Actually, this is omega n square root of k by m. If anybody asks you to the derivation for natural frequency omega n equal to square root of k by m, then you can use this method. Potential energy equal to kinetic energy. If potential energy equal to kinetic energy, then only you will get continuous oscillation. See, you are getting continuous oscillation because kinetic energy equal to potential energy. This is another important formula. Next, free damped vibration. Damped means there is a damper like this. In previous example, there is no damper C, but here I have attached C. Then the equation of motion mx double dot plus cx dot plus kx equal to 0. So we added an extra term cx dot. This is nothing but F is equal to CV. CV is nothing but cx dot. So extra we are adding one term. So how do you solve this equation? Apply Laplace transform on both sides, then ms squared plus cs equal plus k equal to 0. This is quadratic equation. We know that any quadratic equation we can solve using minus b plus or minus square root of b squared minus 4ac divided by 2a. So what is b? C by m. What is a? 1. What is c? K by m. When you apply this, you will get S equal to minus C by 2m plus or minus square root of C by 2m squared minus K by m. Here, this is plus or minus. Because of this, you will get multiple answer. The entire answer depends on this square root value. c by 2m squared minus k by m. It may be 0, negative or positive. There are three possible answers for c by 2m squared minus k. If it is 0, then what happened? Imagine this value is 0, then what happened? C equal to 2m omega n. Then omega n equal to square root of k by m. This is called critical damping. This condition is very important. There is a constant eta. We can take eta as C by Cc, the ratio of C and Cc. If it is 0, then the corresponding damping is called critical damping. Then there is a constant between C and Cc, that is nothing but Cc 2m omega n. Substitute here. So eta plays a major role in the behavior of free damped system. Now apply this formula here. What happened? What is eta? Eta omega n equal to C by 2m. So move this omega n here. Eta omega n equal to C by 2m. See here, I have C by 2m here. That will be replaced by omega n. Then C by 2m, eta omega n, k by m, omega n square. Again, omega n common, I can take omega n outside. So minus eta plus or minus square root of eta squared minus 1 into omega n. So that here, what is the reason for using this formula? Very simple. Here, there are four unknowns. C, one unknown, M, another unknown, K, another unknown. There are three unknown. Whereas here, only two unknown, eta, omega 1. That is why we are simplifying everything. So S value depends on eta and omega n here. Whereas here S value depends on three parameter. That's why we are simplifying everything. So with this simplification here, you have to remember this formula Cc and eta. This is very important. This is the behavior of free damped vibration system. There are three possibilities. This is under damped. This is critical damped, over damped. All these depends on eta value. Eta less than 1, eta equal to 1, eta greater than 1. As I said in the previous slide, eta plays a major role to find the behavior of free damped vibration. Under damping, over damping, critical damping. Under damping means over a period of time, the vibration will decrease. This is under damping. Case 1. Over damping. The word itself, there is a meaning. Over damping. So it will behave like this. There is a gap. It will never reach the equilibrium position. This is over damping. Critical damping means the system reach the equilibrium position as quick as possible. Critical damping, where eta equal to 1. These are the three behaviors of free damped vibration from the equation of motion. Logarithmic decrement. Then this is another important formula, ln of x1 by x2, which is equal to, again we are writing logarithmic decrement in terms of eta, 2 pi eta divided by square root of 1 minus eta square. This is the only formula you have to remember in vibration. Again, logarithmic decrement depends on eta. Once you know eta, you can easily find all the other parameters. Then the difference between damped vibration and natural frequency. This is damped frequency. This is natural frequency. What is the difference between these two? Omega d always less than omega n. Omega n, natural frequency, always higher because the moment you add damping, frequency will decrease. This is the relation. Again, eta plays a major role. Omega n square root of 1 minus eta square. Same this formula. The denominator will come here. So these are all the basic formulas related to vibration. Once you remember these formula, you can solve any problems related to vibration.